Okay, so we've talked about how to deal with the significant digits and the numerical part of a measurement, but we know that measurements have two parts, the numerical part and the unit. So now let's talk for a few minutes about the different units we can have. So in chemistry, we just try to stick with the SI units. So SI is an international system that tries to standardize units across the world. So you'll find that a lot of the units of measurement that we use in the US, like feet, miles, inches, aren't SI units. So we'll try to stay away from those. There are 7 SI basic units that we'll use in this course, or not really in this course, in science in general. So you have a little table in your notes. Let's go ahead and fill it out. So the first column is quantity. So that's just what does the unit even measure. The next column is the standard unit. So what is the standard unit of this quantity that we measure? The next column is the abbreviation. I'll abbreviate abbreviation to save space. Then the last is the base unit. So that is, without any prefixes, what is the base unit for this measurement? So go ahead and think about what are some of the things that we measure. Try and list out as many of the 7 as you can. So pause the video and take a second and see if you can list some of the things that we measure quite often. Okay, so hopefully you came up with mass. We measure mass quite often. Length. We measure length. We measure time. We measure temperature. And we measure amount. So you might be thinking mass and amount kind of sound a lot alike, but they're different. So think about if I ask you about the mass of the students in the classroom. Okay, you could add up how much each of them weigh. But if I ask you about the amount of the students in the classroom, you would count them. So amount deals with counting, the number of things that you have. So these are the 5 that we'll use in chemistry. Let's talk about these, then we'll throw the last 2 in at the very end. So the standard unit for mass is a kilogram. Okay. So I guess I should have written that out. I'll write it down here. So you can reverse those 2. Okay, so the standard unit is a kilogram, the abbreviation for kilogram is a kg, and the base unit is a gram. So, or a little g there. So length, the standard unit is a meter. Okay, you'll see it a slightly different spelling in some countries, but we'll go with that spelling. The abbreviation for meter is just a lowercase m, and the base unit is just meter. Okay, for time, the standard unit is a second. The abbreviation is a lowercase s, which is important. This lowercase capital S stands for entropy that we'll discuss in the second semester, and the base unit is just a second. Temperature, the standard unit is a Kelvin. The abbreviation is a capital K, and the base unit is a Kelvin. So you can go ahead and make a note up here, degrees Celsius plus 273 is equal to Kelvin. Okay, so to convert from Celsius to Kelvin, we add 273. Then the last unit, amount, which is the focus of a large part of this course. The standard unit is a mole, M-O-L-E. The abbreviation is M-O. Because it's pretty rare to see the word M-O out, you'll almost always just see them spelled M-O-L. And the base unit is M-O-L. So those are the 5 that we'll use. The 2 other units that are considered SI units are electric current. The standard unit is an ampere. The abbreviation is a capital A, and it's an ampere. Then luminous intensity. The standard unit is a candela. the abbreviation is a CD, and the base unit is CD. So those are used to measure electricity and light. If you take physics, you'll use those, but for this class, we're going to focus mostly on the first 5. Be aware of the last 2 units, but don't worry about the abbreviations or anything. We won't use those in this course. So those are the units in the SI system that we'll use. But there are other SI units. These are called derived units. So derived units are units that are created by combining other units. So think about something like velocity. Velocity or speed would have a unit of meters per second. Okay, so that would be a unit derived from multiple other units. Or something like area of a 2D shape, you can have meters squared. Or if you had volume, you can have meters cubed. Okay? So this is a time to throw in a little conversion factor here that we should know. A cubic centimeter is equal to a milliliter. So go ahead and write that down in your notes. We'll come back to that in a couple of videos, talk about that more. But the most important derived unit that we're going to talk about for a while is density. Okay, so density is equal to mass divided by volume. Okay, so that's our formula for density. So the most common units for density that we'll see is grams over cubic centimeter or grams over milliliter. So you'll see those are derived from the SI units. A cubic centimeter can be derived from a meter, and a gram from the base of kilograms there. So if I just have the formula density equals mass divided by volume, hopefully we can do some pretty easy algebra and solve for all the variables here. So let's just go ahead and solve for mass. So density equals mass divided by volume. That can also be written as mass equals density times volume, or volume equals mass divided by density. So hopefully you recognize all 3 of these formulas are the exact same. They were just manipulated using algebra. So when we're given a problem involving density, what we want to do is we want to start with this formula, and we want to rearrange algebraically into the correct formula that we need. So let's go ahead and look at the first problem in the notes. What is the density of a block of marble that occupies 310.0 cubic centimeters and has a mass of 853 grams? So we can go ahead and use the original formula here because I'm asking for density. So I have density equals mass 853 grams divided by 310.0 cubic centimeters. So in the calculator, I do 853 divided by 310. So I'll write out everything I get. I get 2.7516 grams per cubic centimeter. So hopefully there should be no question now about how do I round this. We know for all the rounding rules in chemistry, we look at the number of significant digits if it was a multiplication or division problem, which in this case it was division. So I go back to the problem. 853 grams has 3 significant digits. 310.0 centimeters cubed has 4 significant digits. I keep the least number, so I keep 3 significant digits. So my answer is 2.75 grams per centimeter cubed. It's perfectly okay at this point if you want to write this number down and then go back and round it. Be sure you put your box around your correct final answer though. So let's look at one more together. Diamond has a density of 3.26 grams per cubic centimeter. What is the mass of a diamond that has a volume of 0.351 centimeters cubed? So I start off with my density formula. Density is equal to mass divided by volume. But this problem asks for mass. So I go ahead and do my algebra and solve for mass. So mass equals density times volume. So then I can plug in pretty easily. Mass equals 3.26 grams per centimeter cubed times 0.351 centimeters cubed. Okay. So hopefully automatically you should recognize, oh, cubic centimeters cancels cubic centimeters. I'm left with grams. Go ahead and do a quick logic check here. Is grams a unit of mass? If you get something that's a unit that's not a unit of mass, you know you did something incorrectly here. So let's go ahead and type in 3.26 times 0.351, and you get 1.14426 grams. But we know we aren't done. We go back and count significant digits. 3 significant digits, 3 significant digits. So I round off to 3 significant digits, 1.14 grams. So then go back and check yourself. A couple of logic checks here. Do I have proper units? Yes. Did my units cancel out? Yes. And then go back and double check your rounding. Does my final answer in fact contain 3 significant digits? And here the answer is yes, so we're correct. So go ahead and try that last problem on your own real quick. You can pause the video. Okay, so hopefully you did the algebra, solved the density formula for volume, plugged in for volume, got 5.6029 milliliters. You saw that this has 3 significant digits, 4 significant digits, so you rounded off to 3 significant digits and got 5.60 milliliters. So hopefully not too difficult. The next thing in the notes I want to throw in really quickly here in this chapter, just touch on it for a few seconds, then we'll bring it back up in a few chapters, is the concept of inversely proportional and directly proportional relationships. So a relationship that is directly proportional, so we'll abbreviate that as DP, when one goes up, the other goes up. So in simple terms, think about, you could say that the outdoor temperature and the number of Gatorades sold at a gas station are probably directly proportional. As temperature goes up outside, more people buy Gatorade. So the opposite of that's also true. When one goes down, the other goes down. When something is inversely proportional, when one goes up, the other goes down. Okay, so think about, in simple terms, something like the number of students in the classroom versus the number of table space you have. Okay, when the number of students increases, the number of tables, or the amount of table space you get, decreases. So those are very simple terms, very simple concepts. We'll deal with those a lot more in depth when we talk about gas laws, and we'll look at them mathematically and the mathematic constants that we deal with that. But for now, I just wanted to throw out the terms to you and let you be aware of what those mean.